Hello physics students. So this is going to be a very exciting video because you're about to expand your physics knowledge, the knowledge of our very ancient and beautiful universe by a tremendous leap. Up until this point, we've been studying what causes electric field, what causes magnetic field. And as I said in the beginning of the course, so far these topics are separate, electric and magnetic field. But really, they're intimately connected as one phenomenon, electromagnetism. So today, what you're going to first learn for the first time is how magnetic field can create voltage. And later in the topic, we'll learn how that voltage, of course, means electric field. So how magnetic field actually creates electric field, not charge. Charge does create electric field. But in this topic, so does magnetic field under certain conditions. So that's one thing, a tremendous expansion of our knowledge alone, which is exciting in and of itself. But another thing that you're going to learn in this video is something that was enormously important for humanity. How do we generate electricity? Electricity is everywhere. We flip the switches, it turns on, plug things up to charge. How did humans figure out to generate, to harness this mysterious effect, to generate electricity so we could pump it through wires, all through cities and continents and into towns and buildings to do what we need to get done? So we're going to learn both those things, the universe, ideas, and also the practical aspects of how we generate electricity. I'm going to start by demonstrating the phenomenon happening. So let me reconfigure the camera to show you this beautiful effect occurring. I'm going to be demonstrating today's principle of generating voltage with just some common wire and some magnets. I'm not going to be using anything that's been manufactured specifically for that purpose, and that means I'm not going to be all that efficient in my effects. In other words, the voltages I'm going to be producing are going to be very small. So to allow me to measure these small voltages with just the wires that I'm going to be using, I'm going to use this device which is called a galvanometer. And one of the things that a galvanometer can do is it can measure very small voltages. It's very sensitive. To demonstrate that, I have here just a single 1.5 volt battery. No one would say 1.5 volts is a lot of volts, but I'm just going to briefly touch the other end of this battery lead here, and you're going to watch the needle deflect to see just how sensitive this galvanometer is. So ready? Here we go. You see the needle slam down to the other end with just a brief touch of 1.5 volts. So this can detect tiny, tiny voltages because 1.5 volts blows the galvanometer right off the scale. So remember in yesterday's video, we learned that magnetic flux was given by this expression. If the B is constant over an area, we could just say BA cos theta, and the area, the angle is the angle between the magnetic field and the area vector. In other words, when the magnetic field pokes through the surface involved, we have magnetic flux, whereas if the magnetic field runs along the surface, we don't have any flux. So maybe it's magnetic flux that generates electricity. So in order to test that hypothesis, I have here a horseshoe magnet, very strong magnet. I have here a piece of iron, and I'm just going to bring it to the horseshoe magnet, and you could hear a very violent attraction. If I had my finger between there, maybe it would even cut it. And look how strong it is. I could pick up the whole, this is a pretty heavy magnet, and I could pick the whole thing up by the attraction of this iron to this horseshoe magnet. So I'm going to use that as my source of magnetic field. I've got my north pole here, my south pole here, so the magnetic field is going like this from north to south. There's a lot of magnetic field pointing this way in this region. What I'm going to do is take a wire coil like this, and I'm going to put it in here, and I'm just going to hold it in place so my hands are free with a little masking tape. So bear with me. There we are. Oops, a little too short. So right now, with this enormous magnetic field that we just saw the evidence of with that little iron bar, we know that there's magnetic field going this way. We also have an area to this wire loop, because I should have shown you before, but basically it's like a coil like this. So we've got B going through this area. We have B times area times the cosine very nearly 0 degrees, because the area and the magnetic field, the area vector and the magnetic field are parallel to each other. So we've got a lot of flux right here. What I'm going to do is hook this now to this very sensitive voltmeter, this galvanometer, and see if I get any electricity, any voltage out of here. So here we are. No change. So flux is not the condition for electricity to be generated. But watch what happens if I remove this tape and I now pull this coil out of this magnet. Now you see the needle deflect. And so it only, if I have flux, it's not deflecting. If I don't have flux and I just have 0 flux out here, it also doesn't deflect. Flux doesn't deflect, 0 flux doesn't deflect. What causes the needle to deflect is when the flux is changing. See that? I went from 0 to flux and I got a voltage. Now I'm going to go from flux to 0 flux, and the needle deflected. Furthermore, you can see that, so what I'm really doing is I'm changing the magnetic field in this loop, and therefore that changes the flux, because if B changes, flux changes on the other side. Now watch what happens when I move this in very slowly. You see the needle deflect slightly and then return to 0 when I'm not moving at all. Then I'll pull it out very slowly, and the needle deflects very little. But if I go in fast, I get a big deflection. If I go out fast, I get a big deflection. In other words, the change, whether I'm gaining or losing, the faster it happens, the more voltage I have. We can express that idea mathematically with the principle of today. Here it is. This is called Faraday's law. I'll write it down on the board, but it says the mth, the voltage in the loop, is equal to, we'll talk more about the minus sign, but the derivative of flux with respect to time. How rapidly the flux changes. It's the changing flux that matters, and how fast you change it to create voltage or electricity. So what I was doing is, as I mentioned, I was changing the magnetic field and changing the flux and getting voltage or electricity. But I could change anything in this flux equation. I could change area instead by leaving magnetic field constant and angle constant. Watch what happens when I change the area. Okay, so I'll put the loop back in. While I'm putting it in, okay, I had a voltage generated. I'm not going to remove this out, so I'm going to leave B through the loop constant. But what I'm going to do is I'm going to crush this. And now look what happened. I used to have area, and then I went to almost no area. So I didn't change the magnetic field. I didn't pull this out of the horseshoe magnet. I changed the area. And now I could, so I got rid of the flux because I got rid of the area, and I had voltage. Then while I bring the area back, I bring the flux back, and so I changed the flux by changing the area. And that made voltage, okay, mth. Another possibility is that instead of changing the magnetic field or the area, let's leave those constant. We could also generate electricity by changing the flux by changing the angle. That also changes the flux, which creates voltage. So what I'm going to do is shape this into a oval kind of shape like this. And maybe I'll turn the magnet like this, and I got to be cognizant of the wires here. So I go like this. Maybe I'll do the wires this way so you could watch closer. So right now, everything's steady. No change in flux, no voltage produced. B, A, cos theta, all those terms are constant. But what I'm going to do is change the theta by turning this loop. And you see that I had flux, and then I lost it. So that was a change. Voltage was produced. Now I don't have flux, and suddenly I have flux again because I brought it back so the angle went from 90 to 0, so I gained the flux back, and I had voltage during the change. And the faster I do it, the more voltage I get. Now here's an interesting thing of what I could do. Suppose I run an axle through this coil, and then I put it on some bearings and I turn a handle here. Watch what happens to the current over here, or the voltage. I turn, and notice the current is oscillating back and forth. What I have here is a very primitive generator of alternating current back and forth. This is essentially what goes on when humans generate electricity in a power plant. If I could spin this around so it spins 60 times in 1 second, 60 times in 1 second, I would be creating the alternating current that we have in our wall outlets, 60 hertz. That's what the electricity alternates at. So, but the problem here is look at the wires they tangled. So if I made such a generator, very quickly the wires would get all tangled up and tear. So there are ways to solve that problem. Remember when we studied the electric motor, I mentioned these brushes contacting, and then as this magnet spun around, then the brushes changed the contacts and maintained contact with the coil by just rubbing different parts of these contact points. You could do the same thing. You could make brushes on this that contact like this, and so when it spins, there's just a little bit of friction on that contact point, but the wires don't tangle. And then if I did such a thing and I had brushes, what I could do is have a little generator taking rotational motion, rotating a coil in a magnetic field, and then what I'm doing is I'm changing the flux because theta is changing, and because the flux is changing, I'm getting voltage or EMF around the loop. So that's the big idea. Any change in any of these variables changes the flux, which generates voltage, and we generate, therefore, electricity by changing magnetic flux. So let's go to the board, and I'll summarize everything. So here's the idea expressed mathematically. Faraday's law, voltage or EMF, electromotive force, what pushes electrons around in a circuit, is equal to the time rate of change of the magnetic flux. And remember, magnetic flux, once again, is BA cos theta, one of the definitions. Now, another sort of non-calculus way to express this same idea is that you could just convert this derivative to a delta. A change in flux per time will give you the average voltage over that time interval. But this is really the heart of the idea. So again, I want to emphasize, beautiful, magical statement right there. Now you may have noticed that in the video or in the demonstration, sometimes the needle went one way and sometimes it went the other way. In other words, there's a direction of this voltage being produced. And of course, in physics, we don't want to just know what the magnitude is. We want to know everything about this new phenomenon. We want to be able to figure out the direction. And that's what we use what's called Lenz's law for. So what is Lenz's law? It's written out here. The current induced in a loop creates a new magnetic field, not the old magnet, but its own new magnetic field that opposes the change in flux of the original magnetic field. So what I'm going to do, create a pause to allow you to copy this down. So let me do that first. Go ahead and copy this down. And then I'm going to go back to our demonstrations now to show you or demonstrate Lenz's law happening or applied. So let me reconfigure the camera again. First, let's figure out the polarity of this galvanometer. Notice the red wire is connected here, black wire is here. I'm going to connect it to the battery again, this being the negative side of the battery, this being the positive, and I'm just going to graze the wire lightly to see which way this needle deflects when current comes into the red wire. So let's see. There it is. So real quick, it deflects to the right if the current comes in on this right side over here. So let's now hook this to this coil, and we're going to practice that Lenz's law for when I pull this coil out of the magnetic field. So right now, we have a lot of flux going this way through the loop from the North Pole to the South Pole. What direction will the needle deflect when I pull this out? Well, this is how we would figure it out. What we would do is we would say, right now the magnetic field is going like this. When I pull this coil out, I'm going to be losing the magnetic flux that goes from your left to right. So then B induced must oppose that change. I'm losing this. That means B induced has to try and keep it going to prevent the loss. B induced goes this way. So which way would the current flow in this wire up here to produce a magnetic field going this way? I use this right-hand rule, right? Current for my thumb, magnetic field goes around the wire like this. So I put my 4 fingers in because that's going to be the B induced, and I see that my thumb up here goes towards you, out of the screen. So the current's going to be going around this loop like this. It's going to be going forward in this wire into the black wire. See that? It's going out this way into the black wire. So when I pull this out, remember the red wire, if it goes in, it goes this way, but it's going to go into the black, so the needle should deflect that way. Here we go. Let's see if it happens. So there it was. It deflected to basically your left. Now, that's again because there was a change. Now what happens when I bring this back in? What's going to happen is, as I bring this back in, I'm going to be gaining magnetic field or flux going that way because I'm going to be putting it into this magnetic region like this. So I'll be gaining B like this. B induced has to oppose that. We're not losing this, we're gaining this. So B induced has to oppose this gain, which means B induced goes this way. So now I use my right-hand rule to figure out which way the current would have to go to make a magnetic field going this way through the loop. So I put my 4 fingers in like this to represent the B-induced magnetic field, and you see that at the bottom my thumb comes towards you out of the screen. So the electricity is going to go around this loop like this time, right? Like this. So it's going to go out this wire, not out this wire, it's going to go out this wire, and this time go into the red wire. And so we should see when I bring this back, the needle to deflect the other way. And there you go. So pull it out, it deflects this way. Push it in, it deflects the other way. So that's Lenz's law demonstrated. So I'm going to go back to the board, continue with the notes, but I just want to say you have to practice this. But at most, it'll be 1 or 2 points on a free response question. So of course, just figuring out which way the current goes can't be all that much. It'll be, as I said, 1 or 2 points. The bulk of it will be calculations. So let's take a look at what kinds of calculations you'll be doing with this, what we call Faraday's law. Okay, so now you have the knowledge. Now we're going to practice so you can be an expert at applying that knowledge. Let's first take a look at a couple conceptual examples so we can practice Lenz's law. So what I have here is a wire loop, and I've got magnetic field coming out of the board. Maybe I've got a bar magnet behind the wall here with a north pole, so magnetic field coming up through the loop. Let's suppose that for whatever reason, I'm increasing the magnetic field. Of course, that creates a changing flux, therefore a voltage. What I want you to do, I'm going to create a pause. see if you could figure out the direction of the current that's induced. Your choices are either clockwise or counterclockwise. So give it a shot, practice Lenz's law. Go ahead and do that now. All right, so here's what you should have said. I am increasing B. Lenz's law says that we need a new magnetic field that opposes that change. So the new magnetic field, opposing this getting bigger, will go into the board. It doesn't oppose it completely and mean that this doesn't actually increase. It still increases, but with a lag, sort of an opposing effect, so it doesn't increase as rapidly as if this loop wasn't here. So there's my B induced. I'll just put B, I, and D subscript for B induced. Now what I need to do is use this, apply this right-hand rule, current, swirl of the magnetic field around the wire to figure out which way the current goes to produce this new magnetic field. Fingers into the board for the B induced. Thumb for the current down here goes like this. So the current down here goes like this and goes around. In other words, the current goes in what we would say the clockwise direction. So there's the I induced. Okay. Second example. We have the same magnetic field, but this time we're going to decrease that magnetic field. All right, obviously it's the opposite way because it's the opposite effect. All right, but let's practice Lenz's law so you get more practice in case you saw this for the first time on a test. I'll create a pause. See if you could use this Lenz's law to figure out that the current there goes counterclockwise. Go ahead and do that now. Okay, here's how you would go through this reasoning. This is getting smaller. So the B induced has to oppose that. How do you oppose this getting smaller? You make more out of the board to prevent this from getting to zero. That means B induced, I'll label it B, I, and D again, and now that I have the direction of the induced magnetic field, I got to find the direction of the induced current with this right-hand rule. So I put my four fingers in the direction of the induced magnetic field coming through the loop, and my thumb over here goes like this. In other words, we get counterclockwise for I induced. So there we go. Last conceptual example, this was changing the magnetic field in my flux expression. What I'm going to do now is change the angle and induce a voltage. So what I have here is a square or rectangle, doesn't matter. I got a loop that's like this in this plane of the chalkboard here, and I got a magnetic field that's running along the surface of the chalkboard. So in the beginning, I have zero initial flux, because the angle between the area vector, which, let's see, the area vector points out of the board like this, and the magnetic field goes along the board, there's 90 degrees, BA cos 90 gives me zero flux in the beginning. Or you could just say none of the field is poking through the surface and running along it, either way. Then what I'm going to do is, as you can see from this arrow, I'm going to swivel this up so this comes out of the board, and this goes into the board, right? So I go like this. I'm pulling this up around this axle. What is the induced current? We could say maybe in this wire. Does it go down or up? I'll create a pause. Go ahead and apply Lenz's law. See if you could come up with the answer. Here's what you should have done. I am gaining magnetic field coming through the loop this way, because as I turn more and more the field goes through, so I get flux going this way. That's the gain, the change. The B induced, therefore, has to go this way. Maybe I'll just put, that's B, I, and D. So a little crammed in there, but you could see the direction of the arrow. Now I use this right-hand rule, current, magnetic field going around. So magnetic field going into the loop this way, the B induced going in. My thumb on this part shows the current in this wire goes up like this. And down over here, you could put another one. It basically goes around the loop. So there is Lenz's law applied. 3 different situations. Let me create a pause to allow you to copy these notes down. So that was a conceptual example, or 3 conceptual examples. Now let's move on to what we call a quantitative example, calculating the voltage induced using Faraday's law, this one here. So let me make some room. Okay, so this is similar to the last conceptual example we did. I've got a loop oriented like this, and so I've got flux in the beginning because the magnetic field's coming through this loop that's a square, 0.2 by 0.2 meters at time equals 0, and at half of a second it's rotated 90 degrees. I guess we need a direction of rotation, so maybe we say it goes like this, you know, so you are rotating this flat in like that, and we want to know the direction of the current induced, the average EMF over the whole time interval, and then the EMF right at the beginning when you first start turning this, and at the end when it's laying flat. So, first thing, the direction. Lenz's law. Let me create a pause, give you a chance to figure that out. All right, here's how you would figure that out. So we used to have, when this goes around like this, the flux was going into the loop like this. In other words, this was the initial flux going into the board like this. You know, it was coming through into this side, which eventually flips this way. So we used to have it going this way. We lost that B. That means B induced has to oppose this loss. And then, therefore, the current induced to create a magnetic field going into the board like this would have to go like this, around like this. Maybe I'll put it here because there's some room up here. I could say I induced goes to the right in the top portion. So I got A done. Now, the average EMF for part B. What I need to do is calculate the initial flux So I have 0.55 milliteslas, in other words, 5.5 times 10 to the negative third Tesla, or negative fourth. Well, maybe I'll do brackets. The area is 0.2 meters by 0.2 meters. And then I need cosine of the area vector pointing this way out of the surface, the magnetic field vector, 0 degrees. So if I multiply that out, I should get 2.2 times 10 to the minus 5. Now, you could say Tesla times meters squared. That's fine. Or you can say Webers. Either one, both 100% correct. That's the initial flux. So the next thing that we need to calculate is the final flux. The final flux is basically 0 because the area vector goes like this and the magnetic field vector goes like this, 90 degrees in the formula, or you could just say none of the field goes poking in or out of the surface, it runs along. Not even any need to calculate, you could just say 0. Now, what's the voltage? What we do is we use Faraday's law, but not as a derivative. And what I'm going to do is just write it like this. You know what? I could put the minus sign in there. That's what delta is, final minus initial. So in the top, I have the final is 0 minus the initial. And that all happened in 0.5 seconds. So when I divide that out, I get the average voltage, average EMF will be there it is. The little symbol on top obviously means average. So delta flux per time gives me the average voltage. Let me create a pause to allow you to copy that example down. Okay, let's move on to the next part. The voltage as a function of time at exact instants. What I'm going to have to do is take a derivative. And that's going to mean I'm going to need an expression for the flux as a function of time. So what I'm going to do is just use BA cos theta again. In other words, I got ahead of myself. Sorry. The theta. The theta actually is a function. Remember from mechanics that you could write theta equals theta, and don't write this down. That's the expression for the angle as a function of time. So what I'm going to do is define this as cos. Well, you could see theta begins at 0 from the picture between the area and the magnetic field. So I could do that. This is also not accelerating. I should have said that it was going at a steady speed. So the angle is actually a function of the angular speed. The radians per second times seconds gives me the radians of the angle of this vector. So what is the angular speed? Well, notice I turned 90 degrees. I flipped like this. In other words, pi over 2 in half of a second. So this is like radians per second. That's my omega. And I'm going to leave this as a function of time. So that just comes out to be pi times t is my theta as a function of time. And now I'm ready to write an expression for the magnetic flux as a function of time. The magnetic field the area, length squared for a square, times cosine of pi times t. The front term is, again, 4.4, or 2.2, sorry, times 10 to the minus 5. We could put the unit of volts here, but I'm going to just leave it off just to leave this. Sometimes units make a complicated problem already more complicated. So there is the flux that changes with time. At time 0, it's this. At time 0.5 seconds, cosine of this it's 0 flux, and on. It's actually a cosine graph, the flux, which is changing, which means there's a voltage produced. So now we can move on to calculating the voltage as precise functions of time by saying that EMF, the voltage, is the negative derivative of the flux that expression. Now, the derivative is to the cosine function. The derivative of the cosine function is negative sine. So we could say this is negative 2.2 times negative sine and that would be true if this pi wasn't here. But because the pi is there, we've got to use the chain rule. In other words, we now have to multiply by the derivative of what was inside the cosine function. The derivative of pi times time to the 1 power is pi times time to the 0 power. In other words, just plain pi. And so we have an expression for the voltage, minus minus goes away, of 2.2, maybe I'll put the pi first. Maybe that'll be, no, 2.2 times 10 to the minus 5 times pi times sine. There is mth. The voltage is a function of time. So it oscillates as this coil is spinning around. Now at time 0, I can plug in 0 into my expression. Zero times pi is just 0. The sine is 0, 0. So the mth at the beginning, when I first start turning the coil, is 0. That's the answer to C, Roman numeral 1, the mth at time 0. So actually, let me clean this up. There. Let me create a pause to give you a chance to copy this down. Let's move on to the last part. So the voltage at half of a second. So this is basically pi over 2 inside the sine function. You plug in sine pi over 2, you get 1. So that then would just be 2.2 times this pi term. I think I have that calculated out for us. 6.8 times 10 to the minus 5. Hopefully I wrote down the right answer. But you would just, multiply that out. A little messy. Let's try. Okay, so there is the voltage. It's 0 in the beginning. The maximum is at half of a second, 6.8 10 to the minus 5 volts. Now the last thing that I want to point out before we summarize is that the voltage, as you could see from this expression, is a sine function. Pi times 2.2 is this value, and then it oscillates as a sine function. So we could actually plot that. And the maximum is positive 6.8. And the minimum would be negative, because that's what the sine function does. Oscillates between positive and negative. And this is going to be our mth in volts. And as a sine function, it goes. And then, of course, keeps repeating. This right here was 0.5 seconds. As we figured out, the sine went up to its peak value. So this is obviously 1 second. This is 1.5 seconds. And this is 2 seconds. Our coil has completed 1 rotation, and our voltage has oscillated through 1 cycle. And as we keep spinning that coil, we get alternating voltage, hook it to a circuit, we get alternating current that oscillates in a circuit. So now what I want to do, first let me create a pause to allow you to copy these notes down. So what I want to do is summarize with another demonstration. So let me reconfigure the camera. Before we finish for today, I want to show you one more example of how we can use this principle of Faraday's law, changing the magnetic flux to produce a voltage in a coil. What I have here is a solenoid. I have the current coming in this side, which if you look closely at the wires, causes the current to spiral around this way. If we use our right-hand rule, thumb going in the direction of the current on this side of the solenoid, we see that the magnetic field is going to be coming out of this end of the solenoid based on the way I have the wires going. If I switch them, it would be going this way. But the magnetic field goes this way. And we could see that right now with no current, I don't have any magnetic effect. I'm not picking up any paper clips. But if I turn the current on, I get magnetic field in this solenoid, shut it off. I shut the magnetic field off. So I can turn magnetic field on and off in this solenoid by turning this dial. What I'm going to do is take another solenoid, which is hollow like this, that fits this solenoid inside of it. and I'm going to hook the galvanometer to it. So I go like this, and actually, you know what I'll do? I'll just go like this, and I'll turn this on so we have, you know, magnetic field like this. You could see that basically this paper clip is stuck to this metal here. So again, I put this on, and I don't get any voltage because flux doesn't produce voltage or current. What produces it is a change in flux. So what I'm going to do is I'm going to shut the current off in this inner solenoid, which will shut the magnetic field off. So what will happen is the needle will deflect. But before I do that, I want to use first Lenz's law to figure out which way the needle will deflect. So the B is going this way. When I shut the current off in this inner coil, what will happen is I'll be losing this B coming through this outer solenoid. That means B induced has to try and keep it going. So it has to be in the same direction as the B we're losing. So which way, this is B induced, which way will the current have to go in this outer solenoid? Well, if my 3 fingers go through the solenoid like this, my thumb at the top of the solenoid points away from you. So I guess you probably can't see. So I get this magnetic field going. This is B induced. My thumb back here goes down. So the current back here is going to go down. It's going to go like this, the current. And if we look at the wires, this wire spirals down this way, and this one comes up this way. So the current's going to come out this way. And so the needle, the current going in here, should deflect this way as I shut the current off. And there you see it, okay? And now we have steady magnetic flux of 0, no voltage produced. As I increase the current back up, I'm going to have the B induced. Since I'm gaining B like this, B induced has to go the opposite way to impose this increasing B. B induced goes that way. The current in this outer loop goes this way across the top of this solenoid. It goes like this. In other words, it comes up the back and goes into the red wire. So as I up this, then we'll see the needle deflect this way. Okay, oops, I didn't do it fast enough, so let me do it again quicker, and you see the needle deflect. Now I go down, and so I can create an alternating current by making that B fluctuate back and forth, and I get that alternating current in this outer coil. So yet another demonstration of Faraday's law and Lenz's law. Also, if I turn this to this region, this part of the dial, but I do it very slowly, I don't get much deflection because, again, the faster I make the change, the more voltage I get. So I go down slowly, and you see a very small voltage produced. If I go up to this same place, I'm going to have the same amount of flux, the same numerator, the same change in flux, but I'll do it in less time. I'm going to get more voltage. So here we go. And you see that the deflection was greater, and I'm going to go down to 0 quicker. So up quicker, down quicker, and I get more deflection because I did it faster. So that is the big idea for today. Physics now knows how magnetic field can produce a voltage if you change the flux, and humans know how to generate voltage or electricity by changing the magnetic flux in the coil, changing either the magnetic field in the coil, the area of the coil, or the angle between the magnetic field and the area vector. Any one of those changes, and you get changing flux, which then produces a voltage. All right, so that's the big topic for today. I hope you enjoyed the physics. I hope you enjoyed the video and the demonstrations. I'll see you in the next physics video.